Today, we're tackling a problem that challenges us to find specific combinations within an array. We need to count special quadruplets where the sum of 3 elements equals a fourth. Can you find all such combinations efficiently? Given a zero-indexed integer array called nums, we need to find the number of unique quadruplets, a, b, c, d, such that a, b, a, c, and d are distinct indices, and the sum of elements at indices a, b, and c equals the element at index d. The challenge is to count all such valid quadruplets. The most straightforward approach is to use 4 nested loops. The outermost loop iterates for a, the next for b, starting after a, then c, after b, and finally d, after c. Inside the innermost loop, we check if the sum of elements at a give b and c equals the element at d. If it does, we increment our count. This brute force method is simple to understand but highly inefficient, resulting in an big O of n to the power 4 time complexity. We're repeatedly calculating sums and comparisons without leveraging previous work. The key insight to optimize this is to rearrange the equation. Instead of looking for nums a plus nums b plus nums c double equals is equal to nums d, we can search for nums a plus nums b double equals is equal to nums d nums c. This allows us to fix c and d, then efficiently check if the required nums d nums c sum exists from pairs a b, where a and b are less than c. We iterate c from index 2 to n-2. For each c, we iterate d from c plus 1 to n-1. Inside this inner loop, we calculate the target value nums d nums c. We then look up this target in a hash map. This map stores the frequency of sums nums a plus nums b encountered so far, where a and b are less than the current c. After iterating through all possible d values for a fixed c, we then update the hash map. We add all possible sums nums a plus nums c into the map, where a is less than c. This way, when the outer loop progresses to the next c, the map is ready with all relevant sums. Let's trace with the example 1, 2, 3, 6. Initially, our map has nums 0 plus nums 1, which is 1 plus 2 is equal to 3, with a frequency of 1. Now, c starts at index 2, nums c is 3. D starts at index 3, nums d is 6. Our target is nums d nums c, which is 6 minus 3 is equal to 3. We check our map for 3. It exists with a frequency of 1, so we add 1 to our total count. D loop finishes. Now, we update the map for the current c. We consider a from 0 up to c minus 1. For equals 0, nums a plus nums c is 1 plus 3 is equal to 4. We add 4 to the map with a frequency of 1. The c loop then finishes. Our final count is 1. The final count for the array 1, 2, 3, 6 is 1. This is correct because only 1 plus 2 plus 3 equals 6, forming a single special quadruplet. You'll spot this pattern when you need to find combinations of 4 elements, and the problem can be rearranged into a sum of 2 elements equaling a difference of 2. Look for opportunities to fix 2 elements and use a hash map to efficiently find the remaining 2. This optimized approach achieves an big O of n squared, quadratic time complexity due to the nested loops for c and d, and it uses big O of n squared, quadratic time space for the hash map in the worst case. This hash map optimization is a common technique for reducing complexity in combination problems. Try applying this pattern to similar array challenges. Don't forget to like and subscribe for more DSA insights.